Welcome to Controls 2. I wouldn't call this advanced controls, but it's more of a continuation of the introduction to controls part. And basically what we're going to do here is we're going to review a few of the control systems that we've seen already. First is the Bang Bang controller. In Bang Bang controller, the output is either on or off, or on, off, and reverse, or right, like forward, off, and reverse. The idea here is that it's a discrete control variable that we are controlling in the system itself. It's like, is the heating element on or off? Is the fan on or off? We don't have control over the speed or the intensity of those elements. It's a stateful controller, so often we're looking at, in the past, is it been on or off? It is something that stores some intermediate state. And it's got the characteristics of a Bang Bang controller are that it has a fixed over and undershoot. It's how long are we waiting? That gives us how much overshoot or undershoot we have between the two states, right? So often in a Bang Bang controller, we've got a sensor of some kind that is measuring the environment. This makes it a closed loop system. We've got the previous control signal that we have brought in, and which also includes the previous state of the system and the set point. Then we have a comparator that says if these two are different, we're going to turn on the heater. If not, we're going to turn it off. And we'll see things like this. We'll have if we go too far past our set point, then it's going to turn on or turn off. In this case, we're turning off the heater. Then the temperature drops down to some lower threshold. Then we turn it back on, and we have this sort of fixed under and overshoot as we go along. The proportional controller, the control variable is continuous. It has, and the output is proportional to the error. That's the whole idea behind a proportional controller. It's very straightforward in that case. The general form is that our control variable is equal to the control constant, the proportional constant, times the error at the current time, plus some base sometimes. We don't have to usually worry about that, but we'll talk about that in a minute. And the problem here is that we have steady state error. Basically, we end up with something that responds to changes in our set point, but it has some offset, some steady state error that we can't really get rid of. We can add a base amount to it to try and get close, but if we change the set point, that target is going to move and we'll end up either undershooting or overshooting. So we talked about in class, maybe there's something else we can do, and that is the integral controller. And basically the idea here is that we, instead of having it proportional to the current error, we want the control variable to be proportional to the total error, the sum error that we're accumulating in the system. So we want to integrate the error, we want to accumulate it over time and make the control variable proportional to the integrated error, right? So the general form here is that from the time that we start measuring, we're going to sum up the errors that we have in the system, and we're going to keep track of those. We're going to total an error over time, and then and then we're going to make our control variable equal to the sum of the total error we've ever seen times the the integral constant in this case, right? So we have a gain, an integral gain that is multiplied by the sum of error over time. So let's try it. So here is my integral controller implementation. So I have my error calculated same as in the proportional system, and then I have created a sum error variable that's part of my class here, so that I'm keeping it between updates of the controller, and I'm just adding the current error to a running total of error, and I'm using that straight up as a constant, as a control variable for this cruise controller, right? So straight up, this is what we see, right? So here we have the thing, and you can see it's kind of bouncing back and forth. It's oscillating, and we have the control system is oscillating down, the error oscillates down, and it hits pretty much on target. It actually does a really good job of minimizing the error. The error is very, very low, and it's very stable. But when we change the speed, if we set it to medium, we see that big jump in the control variable and it thrashes up against the higher limit. That's because when that instantaneous change occurs, we get suddenly a whole lot of accumulated error. So the this is an overtuned or an underdamped system, which we can modify just by making this constant much smaller. So if we do that and run it, you'll see that it converges. It doesn't oscillate as much, but it's really slow to sort of settle down, right? So we had a big spike in error, but we're eventually dead on, right? So this says that this is the part that will allow us to catch up with whatever our error setting is. So if I set it to medium, it spikes out and then it slows back down again. So we overshoot a little bit, but we dampen down. So in play with a proportional controller, maybe we can integrate these two together and make something that takes advantage of both of their strengths and minimizes their weaknesses. So typically integral controllers that are tuned well look like this. They have a very slow rise to the set point, so the rise time is very, very low, but they don't overshoot and they stay below. And this is really what we want from the integral controller. We want it to respond slowly and over time so that we close the gap with the set point over time rather than sort of instantaneously. So this is the slow response part. Right? A PI controller is just the two added together. So here I've got a proportional controller, which is the error now, added to the output of an integral controller, which is the error over time. And if we combine those in the system here, so my level is going to be KP times error plus KI times some error, and I'm going to make my I'm going to make this lower because that's an oscillating case. If we try this out, we'll see that we saw that it went straight there. It did a really good job, actually. So if we go real fast, if we set the set point high, you see that we have very little overshoot, and eventually it settles almost directly on the error position. So if we drop it back down to a midpoint, we drop down our control, and it hunts really closely to the location that we're looking for. So this combination of a proportional controller and an integral controller does a really good job of sort of balancing out the immediate response of the proportional controller and the slow gap closing of the integral controller, and we get a controller that responds very quickly to changes in the system without a lot of overshoot. And you can see that was a big change. So the accumulated error pushed it a little bit past, so we had a little bit of overshoot. The settling time is a little low because we're slowly dropping down, but it's pretty good. It's actually doing a really good job of keeping us on track. That's the two strengths of these two types of controllers combined into one. So a PI controller, or a proportional integral controller, looks like this, where we've got the proportional constant times the current error added to the integral constant times the sum error over time. Now, the response of a PI controller that's fairly well tuned is going to be pretty good. We saw in the cruise control simulation that it goes really close, it goes straight there, and it gets really on target very quickly. That's a system that has a very low delay in the overall system, so we don't get a lot of overshoot or anything like that. Often a PI controller will have a little bit of overshoot, and you'll see a little bit of wiggle before it corrects. And that's kind of what we see here in this PID loop simulation. The next version is the PID controller, and this is the proportional integral derivative controller. We see the same two control elements. We've got the proportional element, we've got the integral element, and now we've added a derivative element, which is just the change in error at the current time. So we look at the previous error and look at the difference between the current error and the previous error from iterations of the system and multiply that by a proportional or a derivative constant. Now, this actually, in some cases, can introduce oscillation, and basically what it helps do is damp down that response. So we end up having something that looks like this. It overshoots, it's pretty aggressive, but it gets right on target pretty quickly, and it damps down any oscillations that we see. So we get a really, really good control system here. The problem is that it's exponentially harder to tune a PID controller than it is to tune a PI controller, and often we can get pretty good if the system complexity isn't super complex.